G'day everyone. Day 8, dim bulb tester. This is one of the dumbest circuits you can possibly build, but it is incredibly useful when you're doing mains work. Particularly say you work with old equipment that might be faulty in some way, or you're building new equipment. Whenever there's mains voltages and a low impedance source of power available, it's useful to be able to have a ballast in series with that. And one of the simplest ballasts you could possibly do is a light bulb, right? So right now in my dim bulb tester, I've been testing some transformers today. So a gentleman sent me this transformer from eBay, but unfortunately he didn't pack it very well, and it suffered some damage in transit. So this insulator is broken. And I thought, well, that probably renders the transformer useless because it'll probably flash over, which it does. But at lower voltages, we can still play around with this. And I was trying to do some of the transformer measurements that our, day 2, 3, whatever it was, transformer measuring stuff was. And it's actually a little bit tricky with a transformer like this, so we'll talk about that. But to bring it up, I, have a Variac here, and I have my dim bulb tester in series. I probably don't actually need the dim bulb tester in this particular case if I have the Variac, but it's always good to have it. If there's a gross short, basically the worst possible thing will happen is that the bulb will turn on full brightness, right? So it's built like this. Mains comes in, there's a switch for safety, there's the bulb. I have it, on a base so that I can change it. This is a 25 watt, is it? Yeah, it's 100 watt, I think. So the most that could possibly pull from 120, right, is an amp. It's actually more like 950 milliamps. But so it's the current limit in the case of a dead short. If there's not a dead short, then the device under test, which plugs in over here, will just see a little bit less voltage. And in most cases, that's fine. Maybe if it's a switcher, it'll try and start up and shut down over and over again. It may just work completely fine as well, because you might still, depending on the the amount of power that the device is pulling, if it's below, if it's a fairly low current, then not very much current will be dropped across the bulb. The bulb, of course, is a non-linear load, and its impedance will go up as it warms up. But for soft starting things or testing for gross faults, this is a very useful piece of equipment. I mean, there's nothing special about the construction, right? I just made it out of metal boxes. Make sure that you connect the mains earth to the metal boxes for safety, but really that's all there is to it, right? Like, active goes through. Active is switched before it enters the bulb for safety as well. You could build it the other way and it would work absolutely fine, but then you stick your finger in the socket, you might get a little bit of a surprise. Other than that, neutral goes straight through. What I probably should have done, and if I did it again, is I would probably bring a loop of neutral out through one of these ports here, and let you put your clamp meter on that, or maybe even just build a current measuring and voltage measuring device into it. That would be handy. So if you want the deluxe version, maybe you get one of those little current transformer and voltage power meters, kind of like I have for the power for this entire lab, and put one of those in the box as well. So, or you could get a kilowatt or similar off-the-shelf power measuring device and just put that in series. But I digress. So Variac, just my baby Variac, it's not my isolation Variac 2. Most Variacs are not isolated; they're auto transformers, so they're hot to mains, right? You can get shocked. I do have an isolation Variac. They're very rare and generally quite expensive. I managed to get one years ago when they were fairly cheap, and I don't think the person that was selling it really knew what it was, but essentially they have to be built with an isolated primary and secondary, but they're extremely handy for these kind of things too when you're doing mains work on the bench. Alrighty, brief chat about the microwave oven the sine transformer. This one, I've unscrewed it so you can take it apart. It's the old style that's potted completely with, I guess it's tar pitch, which makes it really difficult for me to try and repair this. If it wasn't potted or completely potted, you might be able to replace the insulator, the feed through here, but like this, it's not really worth it. The transformer, though, is electrically intact. There's nothing, as far as I can tell, wrong with it, but I had great difficulty measuring its secondary properties. So I had a couple of different goes at this, and to make sure I wasn't screwing up or my meter was dead, I actually dug out this gigantic transformer that I have, and I measured it. And where are its properties? Right here. Okay, so this is the basics of what I measured. Primary looks like 560 millihenries. You short the secondary, it looks like 519 microhenries, and it's 120 milliohms DC resistance. Do the math on that, you get a coupling coefficient of 0.9995, basically perfect. You look from the secondary, you see 91.3 henries. You short the primary, you see 31.49 millihenries. It's 9.2 ohms. That also gives you a coupling coefficient of 0.9995 and a little bit, so pretty darn close to perfect. The turns ratio, if you divide these inductances and take the square root, is 12.7, which is kind of an unusual transformer. So if this was 120 volt, it'd be like 120 volt to like 1524 volts or something like that. Not entirely sure what this transformer was for. It doesn't have any compliance plating on it or anything, but the core appears to be a wound core. It's super weird. It's also got this other filament here that comes out, and it's shorted to the core, but it's not the center tap of the secondary. The center tap of the secondary is actually under here. I don't really know what this was or why someone set it up like this, but it has, yeah, some nice insulators. And yeah, but it's a cool big piece of iron for doing this math. So basically, this is what it would look like electrically. It looks, 120 milliohms series resistance. The leakage reactance on the primary is like 260 microhenries. You've got a transformer that's essentially 1-to-1 at that point, and 91.3 henries out and 41.9 millihenries leakage on the other side with about 5 ohms. 9.7 ohms. So yay, math works. We analyze the transformer, and it is kind of consistent with what I understand with this transformer and what I measure by injecting a signal into one side. I get the turns ratio that is about 12.7. So when I tried to do this for the neon sign transformer, I had much greater difficulty. So I suspect what the problem is that my meter, my El Cheapo meter here, is not actually very good at measuring like kilohenries. The primary, when you look into it, is here. It's about 1.92 ohms. It looks like about 18.85 henries, and it goes down to 13.04 henries when you short the secondary. That's a coupling coefficient of 0.555, which is not surprising really. So this is ultimately a shunted, magnetically shunted device, because the neon sign that it's connected to will have a negative resistance characteristic. Once it's ignited by the open circuit voltage, and it actually ionizes the gas inside, then it will look like a fairly low impedance. The exact resistance, you can do the math on that. But the open circuit output voltage of this transformer when fed with 120 would be 7,500 volts, I believe. Is that what the compliance plate says here? Yes, 7,500 volts. So it says 225 VA as well, and it's a 30 milliamp rated transformer. That is literally like 30 milliamps times 7,500, which I was a little bit suspicious about. I didn't measure the short circuit current at the full, the full drive voltage, but I did measure the short circuit current, the input currents over range, and they're kind of consistent with what you'd expect for the transformer. But the secret is that there's quite a large amount of leakage inductance. So by having a large amount of leakage inductance, the short circuit current is limited. So even if you completely short circuit the output, people use neon sign transformers for Jacob's ladders, and you can literally short the output. As you can see here, I have a shorting lead across it when I was doing some of my measurements, and it will happily tolerate that all day. The center of this winding, of the secondary winding, is actually grounded. So the case is ground. There's a ground screw here. So there's, only 3,750 volts each side to ground, and it kind of reduces the insulation and the shock hazard of the transformer. And almost all neon sign transformers are built that way. Obviously, modern ones are completely different. They're a switching ballast, and they'll be much smaller because of the higher frequencies. You need less inductance. You need less core material essentially, and they have fancier things like they do current limiting on the primary side, and they can do all kinds of interesting features. Some of the fancy ones can do high-speed flashing, which these transformers are actually pretty good at compared to some of the ones that aren't designed for high-speed flashing do not tolerate that very well and will blow up very quickly. But yeah, anyway, the more I played around with this transformer and tried to make sense of it, I got some really nonsensical answers. But what we can definitely measure is, this is the primary current, and this is the primary voltage that, the primary current that you get at this voltage. So that was kind of interesting. That's with both high tension outputs just shorted together, and this is with just one shorted together. Kind of what you'd expect, right? Half the output voltage, so half the current and the reflected. But the more I kind of did the math on this transformer, I'm convinced that either the capacitance here is messing up my meter, or in general my meter just doesn't like measuring into this. Well, the phase angle is not actually that crazy. Like if this was like 1,000 henries, a 4.7k-ish or 7.2k resistor each side of that wouldn't be ridiculous. Anyway, I'm going to play around with this a bit more, and I might x-ray this or dissolve out some of that pitch, but it doesn't really seem worth it. I have plenty of other neon sign transformers. It's just unfortunate that this one broke. It's in transit, but the gentleman was kind enough to refund me completely, so I can't be too unhappy with him. Yeah, anyway, a little bit of practical work today, and dumbest piece of test equipment around, but extremely useful. You should build one if you don't already have one. Alrighty, see you tomorrow. Bye.